Take a deep breath, let it out slowly. And imagine this, a place so cold, even atoms forget how to move. Somewhere at the edge of physics and philosophy lies a temperature so low, it's almost beyond imagination. A place where time stretches, particles stand still, and the universe itself seems to whisper in silence. Welcome to the story of Absolute Zero. Tonight, we'll float gently through quantum mysteries, cosmic chills, and the strange stillness that lies at the bottom of the thermodynamic scale. But before we descend into this frozen wonder, make sure to subscribe to the channel, tap that like button if you love slow, soothing science, and leave a comment below telling us where in the world you're listening from tonight. Now, wrap yourself in a blanket of stars. We're about to explore what happens when everything comes to a stop. Far beyond the warmth of our everyday world, beyond the frost of winter and even the chill of outer space, there lies a frontier so cold, it reshapes the rules of reality itself. A place where heat becomes a memory, movement fades to stillness, and even time seems to lose its grip. This place has a name whispered in laboratories and written in equations: absolute zero. It isn't just the lowest temperature, it is the limit, the bottom of the thermodynamic well. A state of matter so still, so stripped of energy, that atoms stop vibrating altogether. Or do they? To imagine absolute zero, one must first leave behind the world of sensation. No breeze, no heartbeat, no hum of electricity, just silence. Not the silence of a quiet room, but the silence of a world where all motion has vanished. A silence so deep it becomes a kind of still music, the frozen hum of a universe on pause. And yet, this frozen frontier is not a place we can simply visit. It exists only as an idea, a theoretical cliff edge we approach but never quite reach. Scientists can cool atoms to billionths of a degree above it, but no one has ever crossed the threshold. The closer we get, the stranger the world becomes. At temperatures near absolute zero, matter stops behaving like matter. It turns ghostly, solid and liquid blur. Gases become something new entirely. Atoms gather into choreographed clouds, moving in perfect harmony, like dancers sharing a single thought. Light changes, time stretches, energy refuses to be extracted. So, why does this coldest place in the cosmos matter? Why does it capture the imagination of physicists, dreamers, and sleepy stargazers alike? Because absolute zero is not just a number on a scale, it is a doorway. A threshold between what we know and what we barely understand. A vanishing point where heat, time, and energy collapse into near nothingness. It is the final boundary of the physical world's fever dream, and the more we study it, the more we discover about the strange architecture of nature itself. Quantum fields, particle waves, and the illusions of solidity all reveal themselves more clearly in the deep cold. But before we can explore these mysteries, we must first ask, what is temperature? What does it really measure? And how does the warmth in your coffee cup relate to the trembling of particles too small to see? To answer those questions, we must begin not with cold, but with motion, because heat is motion, and where there is no motion, there may be no heat at all. In this journey, we will travel from the warmth of atoms to the edges of quantum reality. We will follow the history of cold, through the work of Lord Kelvin and the legacy of Bose-Einstein. We will visit the coldest places in the universe and the laboratories that mimic them. And we will ask a question that echoes like frost in the void. What truly happens when everything stops moving? Settle in, stay warm, and drift with us into the science of silence. Not everything we feel is what it seems. When we say something is warm or cold, we're not just sensing an object, we are witnessing the invisible dance of atoms beneath its surface. Temperature is not heat. Temperature is movement, a subtle, invisible motion. It's the quiet trembling of particles, the jitter of molecules too small for the eye to see, a ballet performed in the shadows of reality. Close your eyes and imagine a single atom. A lone sphere suspended in an invisible sea. It doesn't sit still, it shivers, it zips and bounces, tugged by an unseen energy that comes from the very structure of space and time. That motion, that vibration, that velocity is what we call temperature. When we touch something warm, we are not touching fire. We're feeling atoms in motion, moving faster, colliding more often, dancing more wildly. And when we touch something cold, it's not the presence of cold we're feeling, but the absence of movement. The particles are slower, their dance is drowsy. Their song fades to a whisper, heat and temperature, often spoken of as twins, are not the same. Heat is energy on the move. Temperature is how fast particles are moving on average in a substance. Heat flows, temperature measures. You could say that heat is the traveler, and temperature is the signpost it leaves behind. Let's go deeper. In a gas, temperature is linked to how fast the molecules are zooming around. In a solid, it's how much the atoms jiggle in place. Even in the densest metal or the gentlest breeze, those atoms are never quite still. They wiggle, they hum. And this motion isn't just poetry, it's physics. The kinetic theory of matter tells us that all matter, from the steam in your teacup to the iron in the Earth's core, is made up of tiny particles in motion. And this motion, it's directly connected to temperature. The faster the motion, the higher the temperature. But what happens as that motion slows? What happens as the energy is drained, bit by bit, degree by degree? Imagine a great dial turning slowly downward, from 100 degrees Celsius to 0 degrees Celsius, to minus 100 degrees Celsius, to minus 273.15 degrees Celsius. The point at which, in theory, all motion ceases. This is absolute zero, but we're getting ahead of ourselves. Right now, we're hovering above it, just exploring what temperature means, not in equations, but in essence. It means the way the universe keeps time, not with ticking clocks, but with the jostling of atoms, the rhythm of heat. It means that when you heat water on a stove, you're accelerating billions of tiny particles, you're increasing their kinetic energy. And when that water boils, you're witnessing the moment that motion becomes transformation, liquid becomes vapor. Motion changes form. And when you freeze it, you're slowing those particles until they lock into crystalline shapes, still trembling, but slower now, more patient. Here's a thought that might help you drift deeper. If everything stopped moving, every atom, every particle, if even the tiniest quiver of vibration vanished, there would be no temperature at all. No warmth, no heat, just silence. Temperature, then, is the voice of motion. It's the murmur of matter, the humming beneath the surface of the world. And that's why we can never see temperature, only its effects. We feel it, we measure it, we sense its echoes, but it remains a hidden rhythm, playing just beneath the surface of everything we touch. Even in the vacuum of deep space, where there seems to be nothing, temperature exists, not because there's air or fire, but because there are still particles moving, still energy flowing in the quiet dark. And if the particles stopped entirely, that would be the end of temperature itself. That would be absolute zero. But no matter how cold we go, how still things seem, there's always a trace of movement left, because motion is stubborn. Energy is restless. The universe doesn't like silence, not complete silence. So the next time you feel the warmth of sunlight or the bite of a cold wind, remember this: you're not just feeling temperature, you're touching the very motion of the universe. You're holding the invisible hands of atoms, dancing. And tonight, as we drift downward into deeper layers of cold, we begin to ask, what lies beneath all that movement? What happens when it all finally stops? Let's keep going. Some numbers are just numbers, but others reveal something deeper, something hidden under the surface of our world. One such number is 0 Kelvin. Not 0 degrees Celsius, not 0 degrees Fahrenheit, but absolute zero on the Kelvin scale, a place not of weather or seasons, but of fundamental limits, a place where the very heartbeat of matter fades to stillness. But how did we get this ladder? And why does it point downward into a place no one has ever reached? To understand that, we have to meet a man named William Thomson, though most would come to know him by another name, Lord Kelvin. In the 19th century, as science was trying to tame the wild chaos of heat, steam, and engines, Kelvin looked deeper. He asked, what if there were a scale, a true scale, that began not with ice or boiling water, but with nature's coldest possible state? He wasn't chasing temperature for comfort. He was chasing limits, the kind that don't bend to geography or opinion. Celsius is practical. It tells us when water freezes, when it boils. Fahrenheit is human, crafted around body warmth and brine. But Kelvin? Kelvin is cosmic. It begins not at freezing, not at burning, but at nothing. No motion, no vibration, no thermal energy at all. The Kelvin scale doesn't dip into negatives. There are no -10 Ks, no icy mornings on -Kelvin days. Because 0 Kelvin isn't just cold, it's the end of cold. The very floor of the thermodynamic universe. It starts at 0 and climbs. 273.15 K is where water freezes. 373.15 K is where it boils, but the 0 on this scale, it's not arbitrary. It's absolute. Let's picture this scale as a ladder. On the Fahrenheit and Celsius ladders, we can move up or down without limit. But on the Kelvin ladder, you can only go so far down, because at the bottom rung, there's nothing below. No more steps. No more movement. Just the end. But here's the mystery. Even though we can point to absolute 0 on the scale, we can't actually reach it. Not in theory. Not in practice. We can get close, achingly close. We've cooled atoms to billionths of a degree above 0 Kelvin. We've watched matter change form, seen quantum ghosts appear, heard the silence grow deeper, but never, ever, 0 itself. Why? Because the universe always keeps a little motion alive. It resists perfect stillness. It keeps a whisper of energy tucked away, something quantum, something ancient. Even at our coldest, there is always a shimmer, and this is part of what makes the Kelvin scale so haunting. It is the only scale that acknowledges a lower limit to reality. No other common temperature scale does that. Fahrenheit and Celsius can go negative forever in theory, but they're just markers on a human map. Kelvin is a map of the universe itself. In laboratories, the Kelvin scale becomes a tool for clarity. No messy minus signs. No need to ask what room temperature means on a blustery day. Instead, you get a clean scale measured from the pure absence of heat. Every value has meaning, not in relation to water, but in relation to the fabric of reality. And yet, the ladder's bottom rung remains unreachable, not because it's hidden, but because the rules of physics guard it with quiet certainty. The third law of thermodynamics says that as a system approaches absolute 0, the amount of work required to cool it further becomes infinite. You'd need more energy to remove that last flicker of heat than the universe can spare. So we climb down the ladder knowing we'll never reach the last step. We name it, we describe it, we dream about it, but we never touch it. Still, the scale is useful, essential even. It gives scientists a way to speak precisely, to measure the cold of space, the chill of helium at cryogenic temperatures, the behavior of atoms in near-perfect stillness. And for us, sleepy travelers through this science of silence, the Kelvin scale becomes more than numbers. It becomes a pathway into the unknown. So tonight, remember this: there's a scale, carved not by weather, but by the edges of physical law, a ladder with a name, Kelvin, and a bottom step that no one can stand on, a ladder that leads to silence, to stillness. To the threshold of nothing. And beyond it, only mystery. Beneath your fingertips, the table feels still. Beneath your bed, the floor holds quiet, the walls don't tremble. The air seems calm, but if you could shrink yourself a billion times smaller, if you could fall into the very heart of matter, you would find a universe in motion. Atoms tiny, invisible to the eye, not resting, not waiting, but dancing. Each one jiggles in place, vibrates with rhythm, spins and collides, following no music but the laws of physics. This is the atomic ballet. And heat, as we understand it, is simply the tempo of this invisible choreography. In a warm room, the dancers are lively. They move fast, they bump shoulders, they leap. The molecules in your teacup bounce wildly against the edges. Gas particles speed through the air, zigzagging without purpose but full of energy. As the temperature rises, so does the intensity of this ballet. Atoms jostle more forcefully, they twist harder, collide faster, stretch farther. Solids begin to melt, liquids evaporate, and gases become nearly impossible to contain. Heat, then, is not something poured into matter, it is energy that quickens this motion, a conductor lifting the tempo of an invisible orchestra. In colder temperatures, the scene slows, the ballet becomes more restrained. The dancers still move, they always move, but the movements are gentle, like a whisper of motion in a dark room. The atoms in a frozen block of ice still quiver. In place, locked into a crystalline grid, each particle bound by invisible hands but trembling quietly, restlessly. Even in this slowed state, the performance goes on. You see, matter cannot sit entirely still. Not yet. Not until we reach the unreachable floor of absolute 0. And so, the ballet continues, in every object, every breath, in the warm glow of a light bulb filament, in the cold quiet of a glacier's core. The universe is not a silent sculpture, it's a moving stage, and the atoms are never still. Different states of matter show us different dances. In solids, atoms hold hands tightly. They vibrate in place, bound by the strength of their bonds. The structure is rigid, but the dancers are not idle. In liquids, the bonds loosen. Atoms still touch, but now they slip past each other, gliding and swirling like partners in a waltz, no longer fixed but not yet free. In gases, the ties are gone. Atoms move independently, chaotically, rushing into open space like scattered dancers across a vast, empty stage. And in plasmas, the energy is so high, electrons break away, turning the dance into something wild and electric. But what happens? As the energy fades, as the heat drains, as we cool matter down, step by careful step, the dancers slow. Their movements become subtle. A whisper of motion remains, but less and less. This is the approach to absolute zero, the lowering of the curtain, the dimming of the spotlight. Yet even here, in the coldest corners science can reach, the dancers don't fully stop. Quantum uncertainty ensures that they still shift, ever so slightly, because stillness, in the quantum world, is never truly complete. The laws of physics allow no perfect pause. To stop completely would be to violate the Heisenberg uncertainty principle, the idea that we can never know both the position and momentum of a particle with perfect precision. If the atom sat perfectly still, its energy would be known, exactly zero, its position, exactly fixed, and that's forbidden. So even at temperatures a billionth of a degree above absolute zero, atoms retain a shadow of motion, a shimmer in the dark. Still, the closer we get, the stranger the dance becomes. Atoms begin to lose their individuality. They synchronize, like fireflies pulsing in perfect rhythm. They fall into quantum harmony, moving not as many, but as one. It's here we find new states of matter, Bose-Einstein condensates, superfluids, quantum gases, phenomena we'll explore very soon. These are the choreographies that only reveal themselves when the temperature is nearly gone. But for now, let us rest in the wonder of what we've already found. That everything we touch, everything we see, is made of particles in motion. That heat is not a substance, but a dance. That temperature is not a color or a feeling, but a measure of how wildly or gently the atoms are moving. So the next time your fingers brush a cold window pane, or wrap around a warm mug of tea, remember, you're not just feeling hot or cold, you're sensing motion. You're touching a moment in the endless atomic ballet, a whisper of the universe's deepest rhythm. And as we drift closer to stillness, as the dancers slow to near silence, we begin to enter a new realm. Next, we'll explore what happens when we near the very edge of heat itself, and how close we've come to stopping the dance. We followed the quieting dance of atoms, watched their rhythm slow, listened to the hush that descends as heat slips away. And now, we draw closer, closer to a boundary we cannot cross. A wall not built of brick or steel, but of physics. We are approaching absolute zero, a temperature so low, it becomes an idea more than a place. A frontier so still, it challenges the very nature of reality, and though we may never touch it, human curiosity has brought us unimaginably close. In the deepest laboratories of Earth, where silence is engineered, and chaos is frozen out of existence, scientists are chilling matter to the edge of stillness, to billionths of a degree above 0 Kelvin. Not with ice, not with wind, but with light, with magnets, with precision that borders on magic. The goal, to touch the silence, to see what happens when motion almost vanishes. But how do you cool something to near nothing? You begin with a trap. Atoms are caught, like tiny marbles in a bowl made of magnetic fields. They hover in midair, not touching walls, not losing energy to their container. Then comes laser cooling, a technique that sounds hot, but is anything but. Imagine shining lasers from every direction, not to heat, but to slow. Atoms moving toward the laser light absorb photons, and those photons push back, like gentle hands. Catching a falling leaf, the lasers reduce the atom's speed, slowing them from hundreds of meters per second to mere centimeters. With each interaction, a little motion is shaved away. The atoms cool. The temperature falls. Then comes evaporative cooling, an elegant idea borrowed from a cup of tea. When steam rises, it carries the hottest molecules away. The same principle is used here. The most energetic atoms are allowed to escape the trap. And what remains? The coldest, the slowest, the sleepest. This process is repeated again and again, a patient peeling away of energy, until what remains is the quiet core of the atomic crowd. Using these methods, physicists have reached temperatures within a few billionths of a degree above absolute zero. To grasp how cold that is, imagine this: if room temperature were Mount Everest, then these atoms are resting just millimeters above the bedrock of the Mariana Trench, a vertical journey not of kilometers, but of orders of magnitude. At these near-zero temperatures, the world becomes strange. Matter enters quantum states never seen at higher energies. Atoms lose their individuality. They synchronize, they overlap. You're no longer observing particles, but waves of possibility. Probability clouds. Quantum fog. The material world, once solid and certain, becomes poetic and elusive. These ultra-cold environments allow us to study some of the most exotic forms of matter ever imagined, from Bose-Einstein condensates to quantum simulators that mimic black holes and the early universe. But they also show us something deeper, that beneath the noise of warmth, there is a simplicity, a hidden language, a stillness that speaks. Still, no matter how sophisticated our machines, how perfect our traps, or how delicate our lasers, absolute zero remains untouched. Because the closer we get, the harder it becomes to cool further. Each decimal place demands more energy, more time, more precision. And according to the third law of thermodynamics, reaching absolute zero would require an infinite amount of work. An impossible task. A paradox wrapped in cold. But that hasn't stopped humanity from trying God in underground labs, in space-based instruments, in isolated cryostats that hum like sleeping machines. Scientists keep reaching downward, not because they hope to reach the unreachable, but because in every fraction of a degree we conquer, new physics emerges. New possibilities arise. The closer we get, the clearer the quantum world becomes. It is as if absolute zero were a mirror, and only by approaching it do we begin to see what lies beyond the surface of the real. These temperatures are not just curiosities, they hold real-world potential. Quantum computers, cooled near absolute zero, where information is processed not with electricity, but with the strangeness of entanglement. Superconductors, where resistance disappears and current flows without friction. Superfluids, which defy gravity, climbing walls and spinning endlessly. All of these wonders live near the edge, just above zero, where the fabric of nature grows quiet enough to reveal its finer threads. So tonight, as we drift through this story, remember how far we've come, from the heat of atoms dancing to the edge of silence where the dance nearly ends. We've chilled matter to within a breath of nothing. We've made time slow. We've bent the rules, but never broken them. And as we peer over the edge, we begin to glimpse something even stranger. What if atoms, when cold enough, begin to merge, to become one? What if matter itself forgets how to be separate? That's what we'll explore next. When most people think of matter, they think of things: a stone, a spoon, a breath of air. Solid, liquid, gas. These are the familiar faces of the material world, each with its texture, its rules, its place in our everyday lives. But near absolute zero, where motion fades and energy sleeps, another state of matter emerges, something so alien, so beautiful, it almost defies imagination. It's called a Bose-Einstein condensate, and it is what happens when atoms stop being many and begin to behave as one. To understand how this strange state came to be, we must travel back to the early 20th century, to a quiet collaboration between two great minds. Satyendra Nath Bose, a brilliant Indian physicist, was studying light and quantum statistics. He sent a bold paper to Albert Einstein, who saw in it something profound. Einstein extended Bose's ideas from photons, particles of light, to actual atoms. What they predicted was this: if you cooled certain types of particles, called bosons, to near absolute zero, those particles would collapse into the same quantum state. They would merge, their identities would blur. They would lose their individuality. Imagine a room full of dancers, each moving to their own rhythm, some fast, some slow. This is how atoms behave in everyday matter. Now, imagine the room growing colder and colder, until the music becomes barely audible. At some point, the dancers all begin to move in perfect unison. No longer many, but one. This is the essence of a Bose-Einstein condensate. For decades, this state of matter remained a theory, too exotic, too cold to be reached with the tools of the time. But then, in 1995, A miracle of modern physics unfolded. At a lab in Boulder, Colorado, Eric Cornell and Carl Wieman succeeded in creating the world's first Bose-Einstein condensate. Using rubidium atoms and cutting-edge cooling techniques, a second team, led by Wolfgang Ketterl at MIT, followed closely after, confirming and expanding the discovery. For their work, they were awarded the 2001 Nobel Prize in Physics. But more than that, they opened a door to a quieter universe. So what does a Bose-Einstein condensate look like? To the naked eye, nothing much, a tiny cloud, faint, delicate, but through the right instruments, it reveals a kind of elegance rarely seen in nature. The atoms within it no longer act like particles, but like a single, unified wave. They are in phase, in lockstep, coherent. If ordinary atoms are like raindrops, a condensate is like a ripple on a still pond, smooth, continuous, whole. This is more than just weird science. It's a quantum phenomenon, made visible on a macroscopic scale. Usually, the bizarre behaviors of quantum mechanics, superposition, entanglement, wave-particle duality, hide beneath the surface of everyday reality. But in a Bose-Einstein condensate, these behaviors rise into the light. You can see quantum mechanics with your eyes, and that changes everything. One of the most astonishing properties of BCs is their superfluidity. When placed in a container and stirred, they do not rotate like ordinary fluids. Instead, they form discrete vortices, whirlpools that obey strange quantum rules. They can flow through tiny cracks without resistance. They climb the walls of their containers. They move with no friction, no heat loss, no entropy. A superfluid inside a beck isn't just cold, it's perfect. These quantum clouds have been used to simulate black holes, to model the early universe, to explore time, space, and the limits of matter itself. They've become tools in the hands of physicists and dreamers alike. But they are fragile, transient, delicate beyond belief. A slight vibration, a whisper of warmth, and they vanish, the atoms scattering back into individuality. To hold a Bose-Einstein condensate is to hold the hush of the cosmos in the palm of your hand. Why does this matter? Because it reveals something fundamental. That when all else is stripped away, when energy is gone, when heat is silent, when motion nearly ceases, matter doesn't disappear. It transforms. It reveals a deeper order, a hidden unity, a kind of oneness that lies behind the illusion of separation. So as you drift deeper into this journey, picture those atoms, no longer alone, but entangled in harmony, a cloud suspended in silence, dreaming in perfect phase, and ask yourself, what else in this universe, under enough stillness, might reveal such unity? What else might become more whole, not through motion, but through stillness? The Bose-Einstein condensate isn't just a new state of matter. It's a metaphor. For peace, for simplicity, for the idea that underneath all chaos, there may be a place where everything comes together. And from that place, we look toward the even stranger questions. What happens to energy at the edge of absolute zero? What happens to time? Do they stop, pause, stretch into silence? In our next chapter, we'll venture into these mysteries, where temperature meets time, and energy dissolves into stillness. There is something haunting about the idea of motion, stopping, of energy fading, of time pausing. Near absolute zero, the universe enters a different rhythm, a rhythm so slow, so hushed, it feels as if time itself forgets how to tick. But does time really stop? Does energy truly vanish, or do they merely sleep, waiting to awaken again? To answer these questions, we must look into the deep relationship between temperature, energy, and the very nature of time. Let's begin with energy. Temperature is a measure of the average kinetic energy of particles in a system. In simpler words, the more something moves, the hotter it is. At high temperatures, atoms race about, colliding, spinning, vibrating. As we lower the temperature, those movements slow. And at absolute zero, 0 Kelvin, we might expect everything to come to a full stop. No motion, no energy, total stillness. But nature doesn't allow that. According to quantum mechanics, even at absolute zero, particles retain a faint whisper of energy, a kind of eternal murmur. This is called 0 point energy. It is the lowest energy a system can have, and it is never truly zero. Why? Because of one of the deepest principles in all of physics. Heisenberg's uncertainty principle. It tells us that we can never know both the exact position and the exact momentum of a particle at the same time. So if a particle had absolutely no motion, we'd know both where it was and how fast it was going. That's forbidden. Therefore, even at the coldest conceivable temperature, the universe must preserve a tiny flicker of motion, a perpetual tremble woven into the fabric of existence. This residual energy is not chaos, it's order, it's structure. It's the last ember glowing in a cosmic fireplace that can never truly be extinguished. This is why we say absolute zero is unreachable. Not because we lack the tools, but because nature guards it, like a secret too pure to ever be fully touched. And what about time? Time is harder to define. We experience it as a flow, a ticking of seconds, a sequence of cause and effect. But does temperature influence time indirectly? Yes. In thermodynamics, time has a direction. This is called the arrow of time, and it points from past to future, driven by the flow of entropy. Entropy is the measure of disorder in a system. And over time, entropy increases. Ice melts, eggs break, stars burn out, but at absolute zero, entropy reaches its minimum. A place where no more disorder is possible. It's a kind of frozen perfection. In this stillness, some physicists wonder, does time lose its arrow? If nothing changes, if no energy moves, if no particles collide, what does it mean for time to pass at all? It's not that time ceases to exist, but it becomes unmeasurable, undetectable, irrelevant. A clock at absolute zero wouldn't tick, not because time is gone, but because there's nothing left for time to act upon. This idea ripples into cosmology and philosophy alike. If time and change are two sides of the same coin, and change depends on energy, then perhaps the absence of thermal energy is the softest version of eternity. No ticking, no aging, just a breathless hush at the edge of forever. And yet, even in this imagined cold, we know something still stirs. 0-point energy remains. Quantum fields continue to shimmer. So time doesn't stop. But it becomes so slow, so faint, it begins to resemble stillness, like a frozen river that still flows, but so gently. You mistake it for glass. As you lie here tonight, and your own energy ebbs into rest, remember, absolute zero is not an absence, but a boundary. It's the place where physics meets poetry, where movement meets its mirror, where time folds into itself, like a page too quiet to turn. In our next chapter, we'll ask another impossible question. Can anything live there? Can life so tangled with heat, with metabolism, with movement survive in a realm where almost nothing moves at all? Let's find out. Can life exist where warmth does not? We know life as motion, breath drawn in and out, blood flowing, cells dividing, a heartbeat, a blink, a sigh. But near absolute zero, everything we associate with life begins to fade. Molecules slow, chemical reactions stall. Enzymes freeze like statues in the dark. So is the cold, that final cold, the end of life, or could something still whisper beneath the frost? Let's drift into the quiet and ask the question that hums like a lullaby in the dark. Can anything be alive, where even time hesitates to move? The nature of life and warmth, life, as we know it, is a heat-driven miracle. Inside every living cell, thousands of tiny reactions unfold like clockwork. Proteins folding, DNA copying, sugars breaking down. These processes depend on energy, on motion, on heat. And yet, not all life lives in comfort. Some organisms thrive in the unthinkable. Some survive the cold. Cryobiology, the study of frozen life. In nature's laboratory, we find strange survivors, tiny beings that challenge our assumptions. In the tundra, beneath Antarctic ice, and inside frozen soils, lie the extremophiles. Organisms that embrace the harsh. Take the tardigrade, a creature smaller than a grain of sand. It can survive near absolute zero by entering a state called cryptobiosis, a kind of suspended animation. It dries itself out, it halts its metabolism, it folds into stillness. And there, in the ice, it waits for warmth, for motion, for life to resume. So life can survive the cold, but not live in it. There is a difference between surviving and being truly alive. At temperatures near absolute zero, life must hold its breath. It becomes potential, not process, a pause, not a pulse. Deep space, the laboratory of cold. No, let us drift beyond Earth, into the quiet chambers of space. There, between stars and galaxies, the temperature falls to just a few degrees above absolute zero. The cosmic microwave background, the soft afterglow of the Big Bang, bathes the universe in a cold, dim light, just 2.7 Kelvin. It is not quite nothing, but almost. In this dark, cold vastness, scientists have discovered possible signs of dormant biology, molecules that resemble life's ingredients on icy moons like Europa and Enceladus. There's no proof of life, but there is possibility. Could life drift through interstellar space, asleep inside comets, wrapped in frozen water, waiting for a sunbeam to awaken it? Some scientists say yes. Panspermia, the idea that life can travel between planets, sleeping through eons of deep cold, is not pure fantasy. Inside meteorites, simple organisms have been found that survive the vacuum of space. Not alive in the cold, but not dead either. Just paused, perfectly preserved. Like a breath held for 1,000,000 years. The cold pause. Imagine this: a seed drifts in space. Its surface is frozen, its heart is still. Around it, no warmth, no wind. Just the hum of distant stars, and the breathless silence of near-absolute zero. It waits, not thinking, not growing, not dying. And then, one day, perhaps by fate, perhaps by luck, a warm planet's pull changes everything. Suddenly there is light, heat, water. The seed stirs. What was frozen begins to live again. Philosophical cold. What is life? In this stillness, we are forced to ask, what is life, really? Is it just motion and heat? Is it just metabolism and replication? Or is it also potential, memory, hope? A frozen bacterium might not be active, but it remembers how to be alive. Its structures remain. Its code is intact. So maybe life is not just the fire, but the spark, even when buried in ash. Artificial life and quantum ideas at the bleeding edge of science. Some researchers imagine forms of life that might not rely on heat at all. Could quantum computers, with their entangled qubits and near-zero temperatures, host patterns of thought? Could artificial minds exist in superconducting cold, where atoms move in perfect unity? It's speculation, but fascinating. Maybe warmth is not the only cradle of life. Maybe the cold is not the enemy, but a different kind of silence we do not yet understand. The still point of survival. Also, can anything live at absolute zero? Not in the way we breathe and think, not with beating hearts and flowing blood, but perhaps something can survive in the stillness, in the pause, in the hush before the next moment begins. Life, it seems, has a way of waiting. And in the deepest cold, where atoms forget how to dance, some part of life still remembers the rhythm. As you drift into sleep tonight, consider this: even the coldest corner of the universe may be cradling a future heartbeat, a song waiting to begin again. Next, let's follow that song into the coldest places we've ever discovered. Out beyond the planets, past the scattered comets and drifting dust, lies a realm so cold it barely remembers motion. A place where time seems to exhale and hold its breath. This is where the temperature of the universe itself settles like fine ash, soft, silent, almost still. What is the coldest place in existence? Not on Earth, not even in our solar system, but somewhere deeper, somewhere darker. Somewhere in deep space. Let's drift there now. The cold fabric of the universe. Everything in the universe carries some warmth. Stars burn, planets radiate. Even you, as you listen now, glow gently in infrared. But in the void between galaxies, away from starlight, away from warmth, space cools toward nothing. The average temperature of the universe is just 2.7 Kelvin, only 2.7 degrees above absolute zero. This chill is the lingering breath of the Big Bang itself, a whisper still echoing across cosmic time. It's called the cosmic microwave background radiation. It is everywhere, filling all of space with the ghostly glow of microwaves, like the fading warmth of a fire that burned 13.8 billion years ago. In every direction, that same soft, cold light meets us, uniform, unwavering, like the lullaby of the cosmos. The Boomerang Nebula, colder than space itself, but remarkably, some places in space are even colder than that average. Take the Boomerang Nebula, a strange, dying star in the constellation Centaurus. This nebula is not just cold, it is the coldest known natural place in the universe. Its temperature, just 1 Kelvin, colder than the surrounding space. How? The Boomerang Nebula is a cloud of gas expanding rapidly from a dying star. As it expands, it cools like the air from a spray can, but on a cosmic scale, the The star's last breath has become a kind of interstellar freezer, plunging gas into near absolute silence. Imagine drifting through it. No sound, no heat, only a frozen wind whispering away from a fading light. The vacuum isn't empty even in the most barren parts of space. The vacuum is not truly empty. There are still particles, fleeting, flickering quantum ghosts that blink into and out of existence. There is still energy, still motion, still time. Even in the dark between galaxies, atoms and molecules shiver, barely moving, but never fully still. This is why true absolute zero can never be reached, not even in the heart of a nebula, not even in the quiet between the stars. There is always something. Interstellar ice and cosmic dust, and even in these cold reaches, the universe is not silent. Clouds of interstellar ice, frozen water, methane, ammonia drift like forgotten memories through the galactic dark. Tiny particles of dust coat themselves in frost, forming cosmic snowballs that may one day become the seeds of planets. These ice grains are among the coldest solids in space. They reflect almost no light. They float and touch for millions of years. If you could hold one, it would feel like holding time itself, still, ancient, patient. Black holes and cold horizons. Ironically, the coldest known entities are found near some of the hottest. Black holes, those gravitational abysses, emit something called Hawking radiation. The larger the black hole, the less it radiates. A supermassive black hole might have a temperature fractions of a Kelvin above absolute zero. You could float just outside its event horizon and be bathed in a nearly perfect stillness, an infinite pause just before the fall. The poetry of cold in deep space. Cold is not just the absence of heat. It is a texture, a character, a presence made of stillness. It wraps the universe like a quiet blanket, allowing stars to shine against its backdrop, allowing planets to cool, allowing life to rest. And in that cold, there is also clarity. No storms, no winds, just the soft hum of gravity and the faint pulse of distant starlight. If you could stand there, imagine yourself drifting in that space, in the void between galaxies. There is no sound, no up, no down, just stars like dust, scattered and far. Your body would not freeze instantly, because there's almost nothing to carry the heat away. Instead, your warmth would slowly radiate outward, photon by photon, like an ember dimming in the dark. And in that silence, you'd feel something unexpected, peace, because this is not chaos, it's the quiet between symphonies, the stillness before creation. So the next time you look at the night sky, remember, it isn't just a sea of stars. It's a sea of cold, and somewhere out there, in the endless hush, the universe keeps its secrets wrapped in frost. Now let's return to Earth for a moment, because while space is unimaginably cold, there is something even colder, our own laboratories. In the quiet lands of deep cold, we've learned to dream of a final destination, a place where all motion stops, where particles no longer buzz or sway, a temperature that is absolute, still, perfect, 0 Kelvin. But the closer we get, the more the universe whispers back, you can come close, but you can never truly arrive. This is the strange, beautiful truth of nature, that absolute zero is not a door we can open, but a horizon that forever recedes. Let's gently explore why. The third law of thermodynamics. In the heart of classical physics lies a quiet rule, one that hums softly through every cooling chamber, every frozen atom, every melting ice crystal. It's called the third law of thermodynamics, and it says, simply, as a system approaches absolute zero, the entropy, the disorder of that system approaches a constant minimum. But absolute zero itself can never be reached through any finite number of steps. Imagine climbing down a staircase that stretches endlessly downward. With each step, it gets colder, the light dims, the motion slows, but there's always another step, another fraction of a degree, another layer of stillness. You can descend forever, but you will never reach the bottom. This isn't just poetic metaphor, it's a fundamental law. Even if we had all the time and energy in the universe, we'd still find ourselves infinitely close, but infinitely far from the final chill, the quantum fluctuations that never sleep. Let's zoom in now, much closer, to the world of particles, where atoms blink and jitter with strange life, even in the deepest cold. Here, another truth emerges. Quantum mechanics won't let us stop the dance. Why? Because of a beautiful principle called Heisenberg's uncertainty principle. It tells us this: you can never know both the exact position and exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. So if we tried to freeze an atom perfectly in place, to bring it to absolute zero motion, we'd violate this rule. An atom perfectly at rest would have zero momentum, but that would mean we know both where it is and how fast it's moving, which is forbidden. Nature doesn't allow such certainty. There must always be a flicker, a wiggle, a whisper of motion, no matter how cold it gets. This is why even the coldest atoms, chilled to billionths of a degree above zero, still vibrate ever so slightly. Quantum mechanics ensures the universe never fully stills. It protects mystery at the smallest scale. The limits of cooling methods. Over the last century, we've grown masterful at making cold. Cryogenic chambers, laser traps, evaporative cooling techniques. Scientists have created tools that slow atoms almost to a standstill. In some labs, temperatures of 0.00001 Kelvin have been achieved. That's less than a billionth of a degree above absolute zero. Staggeringly cold. Colder than interstellar space. Colder than the Boomerang Nebula. Colder than anything the natural universe can offer. And yet, even with all our knowledge, with the most advanced machinery on Earth, we always fall short. Why? Because every cooling technique eventually hits a wall. There's always some stray energy, a rogue photon, a vibration in the lab walls, a pulse of electricity from a machine. To reach absolute zero, you would need to remove every last speck of energy, perfectly, completely, forever. And that, physics says, is not possible. Nature preserves motion. There's a hidden elegance in this impossibility, a kind of cosmic wisdom. If all motion stopped, if every particle were fixed in place, then the laws of physics would freeze, too. Time would lose meaning. Cause and effect would dissolve. The universe would become a painting instead of a poem. But nature resists stillness. It clings to motion like breath. Even in the most silent corners, it keeps a heartbeat pulsing. Maybe this is not failure. Maybe it's design. The inability to reach absolute zero is not a flaw in our science, but a signpost in the architecture of reality. Everything must move. Everything must change. Everything must stay just warm enough to live. The eternal pursuit. And so we continue. We build colder chambers. We test deeper theories. We cool atoms to new records. But absolute zero remains just out of reach. Beautiful idea, a ghost of perfection. Still, it guides us. Like a star behind a cloud, it gives us direction. And though we may never touch it, we'll always be drawn to its mystery. So when you hear that haunting term, absolute zero, know that it is not a place, but a pursuit, a reminder that some things are meant to be approached, but never held. Not all frontiers lie in space. Some stretch inward, into silence, into stillness, into temperature so low you can barely call it heat at all. Tonight, we journey not to the stars, but into the quiet corners of Earth, where humankind has chased the cold to its most delicate extreme. These are the coldest laboratories on Earth, places where reality softens, and matter whispers secrets that only the cold can hear. Beneath the ice, the South Pole and cryogenic curiosities begin at the bottom of the world, Antarctica, where even nature forgets how to stay warm. Beneath the thick, white skin of ice, scientists have built instruments not just to survive the cold, but to go colder still. The Ice Cube Neutrino Observatory, embedded deep within the Antarctic ice, doesn't study temperature itself, but it operates in some of the coldest natural environments imaginable. Here, particle detectors sleep in the ice, watching for rare neutrinos that glide through the Earth. These elusive particles thrive in cold silence, unbothered by heat, traveling through solid rock like whispers. While Ice Cube doesn't push toward absolute zero, it is part of a global chorus of experiments that live and breathe in the frost. But deeper cold is made not by nature, but by human hands, inside the lab, chilling with lasers and magnetic traps. In the world's coldest research centers, scientists play the quietest of games, slowing atoms, catching them, holding them still with light and magnetism. At places like MIT, Harvard, and the Max Planck Institute in Germany, physicists use techniques like laser cooling, magnetic evaporation, blur cooling. Here's how it works, softly explained. Atoms move fast when they're hot. So to cool them, scientists shine precisely tuned lasers at atoms, slowing them down by absorbing the photon's momentum. It's like trying to stop a rolling marble by tossing ping-pong balls at it, each one pushing, nudging, slowing. With enough precision, atoms can be cooled to within billionths of a degree above absolute zero. In these chambers, the temperature drops to nanokelvin ranges. That's 0.00001 Kelvin. This is where the fabric of quantum behavior becomes visible. This is where atoms begin to sing the same quantum note. The coldest temperature ever achieved in 2021. Scientists at the University of Bremen in Germany briefly achieved the coldest temperature ever recorded on Earth, 38 trillionths of a degree above absolute zero. That's 0.0000038 K. They did it using a free-fall chamber, dropping a magnetically trapped gas of atoms inside a tall vacuum tower. In that fall, all external disturbances vanished. For a few precious seconds, the atoms were suspended in near-perfect silence. No sound, no friction, no interruption. In that moment, those atoms were colder than anything in the known universe. Colder than the vacuum of space, colder than the Boomerang Nebula, colder than time itself. Nobel-worthy cold. Some of the greatest scientific breakthroughs in the last 50 years have come from chasing absolute zero. In 1995, Eric Cornell and Carl Wieman at the University of Colorado created the first Bose-Einstein condensate, a new state of matter only possible near absolute zero. It was a shimmering cloud of atoms, all moving as one, not just cold, but quantum cold. That moment won them the Nobel Prize in Physics in 2001. Others followed. In 2017, a team at NASA launched the Cold Atom Lab to the International Space Station, where cooling atoms in microgravity allows for longer observation times. Without gravity pulling atoms out of the trap, up there, in orbit, atoms can linger in the cold for seconds instead of milliseconds. The universe gives a helping hand, a longer lullaby for particles at the edge of sleep. Why do we chase this cold? You might wonder, why go to such effort? Why build machines the size of rooms to lower temperatures by billionths of degrees? Because in this quiet realm, quantum physics reveals itself. Near absolute zero, you can create superfluids that flow without friction. Observe quantum tunneling with clarity. Witness entanglement and collective atomic behavior. Simulate the early universe. Build more stable quantum computers. In the cold, reality becomes transparent. You can see laws that are normally hidden by heat and noise. It's like turning down the volume of the cosmos until only the deepest truths remain. The dream of perfect stillness. Coldest laboratories on Earth are not just engineering marvels. They are meditations in metal and magnetism. Inside them, scientists play lullabies for matter. They coax atoms to sleep, to gather close, to hum together in quantum unison. They listen for the softest answers to the biggest questions. And though absolute zero will never be touched, these labs come close enough to change our understanding forever. There is a place beyond motion, beyond heat, beyond sound, beyond time, a temperature not just measured in numbers, but in absence, in the stilling of atoms, the silencing of the very breath of matter. Tonight, we arrive not at a lab, not at a nebula, but at the edge of understanding itself. This is not just about physics anymore. This is about what it means to be still. To be nothing, and in that nothingness, perhaps, to finally know peace, a temperature that becomes a thought. When we speak of absolute zero, we speak of a scientific limit, but also a human metaphor, because what is zero, if not the place we all wonder about, a place of total silence, total surrender, and of joint beginning of being in this strange frontier. Temperature becomes almost spiritual. What happens when movement stops, when entropy disappears? When time holds its breath? Is this what death feels like, or birth, maybe, in reverse? The stillness between stars. Look up into the night sky. What do you see? Stars, yes, bright, burning, beautiful, but between them, vast oceans of nothingness, colder than your thoughts, quieter than your fears. In that space, the universe expands in silence, and yet, even there, absolute zero is never reached, not in the deepest void, not in the loneliest crater, not even in the quietest lab. It is a reminder. Stillness is an idea, not a destination. The human longing for quiet. Have you ever longed for everything to stop, not in despair, but in rest? To step outside the ticking of clocks, the humming of electronics, the buzz of whirring. To feel nothing. This is what absolute zero offers, not as a physical place, but as a mirror for the soul. It invites us to imagine a place where no choices must be made, a mind untouched by thoughts, of self without movement. In the poetry of physics, this is the closest science comes to meditation. What is something without motion? At temperatures near absolute zero, particles lose their individuality. They merge. They become waves. They stop being as we know it. If movement defines identity, What happens when movement stops? Who are you when you're not thinking, not acting, not feeling? Are you still yourself, or something wider? These are not questions physics can answer, but they live in the same room as Bose-Einstein condensates, as entropy collapse, as motionless atoms wrapped in quantum fog. Time without ticking time, too, depends on motion. Clocks tick, hearts beat, stars rotate. But at absolute zero, the concept of time begins to blur. If nothing moves, how can time be said to pass? In some interpretations of quantum thermodynamics, time is emergent, a result of entropy increasing, but at zero entropy. No increase, no arrow, no before or after, only now. Forever now. A single frame of an eternal film, the beauty of the unreachable never reach absolute zero. We know that. Nature forbids it, but perhaps that's the point. Like perfection, like nirvana, like stillness of the heart, it is the striving that matters. To move towards stillness is to understand what movement means. To seek zero is to know the meaning of one. Every experiment, every cooled atom, every sleepless scientist, they're chasing not a number, but a philosophy, the desire to touch the edge of meaning. Rest as a scientific principle in your body. 2. There is thermodynamics. When you sleep, your energy use drops. Your entropy reorganizes. You move toward order. Rest, then, is a kind of personal cooling. Not to zero, but to peace. Perhaps this is why we're drawn to the thought of absolute zero. It's not death we seek, but release, from noise, from chaos, from expectation. A place where we can finally just be. The quiet that lives inside you. So now, imagine again, a room with no heat, no time, no noise. You sit there, not moving, not thinking. Atoms no longer buzz. Ideas no longer spin. You've reached your own version of absolute zero. And in that moment, you are not gone, but deeply, purely present, perfectly still, perfectly whole. There are stories that end with answers. This is not one of them. This is a story that ends in a hush, a silence not of nothingness, but of everything finally at peace. We have traveled far, from the buzzing dance of atoms to the coldest places in the universe, from quantum stillness to the philosophy of zero. Now, we arrive not at a final fact, but at a feeling, the feeling of the endless chill, a place that isn't a place absolute. Zero is not a destination. There is no door to open, no signpost saying you have arrived. Instead, it's an idea, a lighthouse on the horizon of understanding. Always visible, never reachable, even the coldest labs, with lasers and liquid helium, can only approach it. Billions of a degree above, close, but never quite there. Because nature, in all its quiet genius, keeps motion alive, even in its smallest whispers. The whisper that never stops. Even in silence, there is vibration. Even in stillness, a shadow of movement lingers. Heisenberg's uncertainty principle says, we cannot know both position and momentum perfectly. So, even when we press matter into stillness, some shimmer of uncertainty remains, a murmur in the fabric of reality. A breath we cannot hear, but it is there, proof that the universe never truly sleeps. The chill within and without. No, let's pause. Not as a physicist, but as a person. What does it mean to get this close to nothingness? You felt it before, haven't you? The quiet after snowfall, the pause between heartbeats, deep calm just before sleep. Those are moments when your own energy cools, when your body becomes a landscape of low noise, and your thoughts float like mist. We seek absolute zero, not just in labs, but in ourselves. It's the deep sigh, the long exhale, the return to center. From science to stillness journey through absolute zero has taught us that temperature is motion, that time is tied to entropy, that energy resists stillness, that even emptiness is full of mystery. We've seen atoms merge into single waves. We've stood inside cosmic silence. We've watched lasers slow matter to a crawl. But now, we leave behind equipment and numbers. We enter a space where science becomes serenity, and serenity becomes science. The chill between stars far out in space, beyond even the Boomerang Nebula, beyond the microwave glow of the Big Bang, lies the dark, so still, it feels eternal. But even there, a photon may flicker, a molecule may drift. The universe is always whispering, never fully quiet, never fully cold. That's the secret, the poetry of it all. Absolute zero doesn't exist in the world as it is, but it does exist in the mind, letting go of heat, of motion, of worries. So now, dear listener, let yourself drift. Let go of heat, Let go of movement. Let go of questions and outcomes and goals. You are floating in the idea of stillness. Not dead, not gone, just here, perfectly still. Perfectly safe. The chill wraps around you not as threat but as comfort, a blanket made not of temperature, but of truth, the truth that not everything must move, that not every question needs an answer, that sometimes the journey is the destination, the chill that never ends will never touch absolute zero. But in reaching toward it, we become more aware of heat, of motion, of life. It is in the contrast that we feel meaning, the dance of particles, the hum of atoms, the ticking of clocks. They are precious because they end. And so, too, is stillness precious because it almost exists, right at the edge. Forever out of reach, forever calling, the endless chill. Not the absence of everything, but the presence of something deeper. If you're still here with us drifting between stars and silence, thank you. If this story helped you sleep, if it made you feel something gentle, something curious, we invite you to stay with us. Subscribe to Science for Sleep for more calm, poetic journeys through the cosmos. Like this video if it brought peace to your night. And tell us below, where in the universe do you dream of visiting most? Tonight we explored what happens when motion fades and stillness whispers. Next time, we'll travel somewhere new, somewhere equally beautiful. Until then, sleep well, dream deeper, and remember, the universe is never truly still, but in its quietest corners, it hums just for you.